everybody. Respected Principal Ma'am, Professor Dr. Shuttapa Mukherjee. Respected Emeritus Professor, Professor Dr. B.N. Chatterjee, Sir. Respected Registrar, Dr. Shubhashish Pradhan. Respected Head of Department of Electronics and Communication Engineering, Dr. Ivy Majumdar, Ma'am. Respected Speaker for today, Dr. Mohana Sundaram, Sir. All the faculty members, technical staff members, participants, and students. I, on behalf of the Department of Electronics and Communication Engineering, BPPIMT Institute of Management and Technology, would like to welcome you all to this webinar series on sustainable energy, organized by the Department of Electronics and Communication Engineering, BPPIMT Institute of Management and Technology. This webinar will expand over 3 days, starting from today, that is 17th of June, till 19th of June, and will host an array of eminent speakers who would share and impart their knowledge, which will provide us all with an opportunity to enrich ourselves. Without much further ado, I would like to invite our respected Principal Ma'am, Professor Dr. Shuttapa Mukherjee, to kindly address the audience. Ma'am, please.
Respected speaker, our Emeritus Professor B.N. Chatterjee, Head of the Departments, faculty and staff members, my dear students, and all the external participants, a warm good afternoon to all of you. And welcome to the webinar series on sustainable energy organized by Electronics and Communication Engineering Department of BPPIMT Institute of Management and Technology. Environmental pollution is of considerable concern throughout the world. We all are aware. Good afternoon. Presently, the entire world is fighting with pandemic, frequent cyclones, tornadoes, rise of sea level, melting of polar ice, whatnot. All the consequences of our careless attitude towards environment. Though we are late, all these phenomena are actually forcing us to think about adopting new technologies to protect our planet. The increasing energy demand has focused attention on sustainable energy supply, which implies optimized use of energy, minimized pollution, and reduction in fossil fuel consumption. From this point of view, I think the topic of the webinar is very relevant. The objective is to provide a platform to acquire knowledge on unconventional energy systems. This webinar series will be held during 17th to 19th June 2021. During these 3 days, as speakers will have Professor Mrityunjay Chakraborty, Professor Siddhartha Mukhopadhyay from IIT Kharagpur, Professor Shubhi Sharkar from Jadavpur University, Mr. Hari Babu, Associate Director, CDAC Bangalore, Disha Bhattacharya, Senior Engineer of Qualcomm, the experts from both academia and industry to enrich our knowledge. I'd like to express my sincere gratitude to the speakers for accepting our invitation. Thanks to the department for choosing such a topic to create awareness. And I'm sure this program will enrich us and will motivate all of us to adopt new policies, to go green, to save our Mother Earth. Thanks to all the participants for joining us. I wish the program a grand success. Thank you.
Thank you, ma'am, for addressing the participants. Next, I would like to take the opportunity to welcome our respected Emeritus Professor, Professor Dr. B.N. Chatterjee, sir, to address the audience. Sir, please.
Respected Professor Shuttapa Mukherjee, our principal, respected guest speaker from CDAC, Bangalore, head of the departments, Professor Ivy Majumdar and other HODs, faculty members of Department of ECE and other departments of BPPIMT Institute of Management and Technology, technical and supporting staff of our institute, our students, as well as the external audiences. It is a great opportunity for me to address you all during this webinar on sustainable energy arranged by Department of ECE of BP Poddar Institute of Management and Technology. As I understand, according to me, sustainable energy means the energy sources which are such that in future generation will not be suffering. Principal Madam mentioned about pollution and other things, means energy resources getting depleted. So these are the basic reasons for work on sustainable energy. As you know, the fossil energy is the main source of energy nowadays. And day by day, our fossil energy sources are getting depleted as well as it is giving more of pollution. And therefore, for a long time, people are trying to use the other sources of energy. As you know, hydroelectric sources, that means water energy, then air energy, they have utilized, geothermal energy has been utilized, nuclear energy has been utilized, and many types of other sources are tried, like solar, solar energy has been utilized. And we can feel that some of these sources are sustainable. For example, solar energy, you can say, is sustainable energy. Then air, we are assuming that windmills and wind power energy is sustainable. Water resources also, you may say, geothermal also, you may say, sustainable energy. Another thing which has been utilized and for which India is the topmost, I can say, in the world, is the biogas, biomass, from the biomass, gobar gas plants, etc. You can see, you will not find anywhere in the world. This is the unique for our country. So these are certain things is the alternate source, but even today, this alternate source constitute a very small part of the overall energy consumption. And that is why even now research work is going on. A few days, a few weeks back, I found a good news from the research work by IIT Madras chemistry department. They did a good research work. In fact, this work is going on around the globe for a long time. That means fuel cells, hydrogen fuel from seawater. They are successful at IIT Madras. So that if that is commercially implemented, I think we are going to have a very good source of alternate fuel, sustainable fuel, assuming that our seawater is not going to end. Similarly, we find very good research work in the area of nanotechnology, particularly carbon nanotechnology for sustainable energy. I exactly don't know much. MIT, Massachusetts Institute of Technology, has done considerable amount of good work in this for renewable energy sources. Is it for exactly production or for such certain purpose it is being utilized, that I don't know, but a very good work is going on. Similarly, there are many other type of work is going on for alternate sources for energy, and gradually people are trying to have lesser burden on your fossil fuels. Fossil fuel, if they can reduce by this, that will be an achievement. I don't know how much time it will take, but definitely it will be done, because for the existence of the human being, if something is getting depleted, alternate source is a must. In fact, this work is going on for many years, maybe more than 50 years or even more. So ultimately, there will be at least 40 to 50% of the other sources which will be utilized. So in this webinar, some idea about this, as well as some of the recent technologies which are used for these alternative sources or sustainable energy sources will be discussed. One lecture is today is use of IoT. IoT is very relevant. Similarly, other things will also be there. Fortunately, BP Poddar Institute of Management and Technology, both IoT as well as nanotechnology, we are doing some work. So we can definitely, as well as materials, we are doing some work. Therefore, we will be able to do some impact in this aspect, as well as we have got a very important department, the Department of Electrical Engineering, where power or energy is one of the major thirst area. So this interdisciplinary work of sustainable energy is definitely a part of our institute, and I congratulate the institute for taking a step of arranging a webinar where we can not only give importance or idea about it, but also it may lead to some direction. And in future, if I see a research group coming out, research or development group coming out, I shall be a very happy person. With these few words, let me wish a very grand success to this webinar and for the future work in this area, in this institute. Thank you very much.
Thank you, sir, for your encouraging words. Next, I would like to invite the Head of Department of Electronics and Communication Engineering, Dr. Ivy Majumdar, ma'am, to share her views with the forum.
Thank you, Rashmita. Am I audible?
Yes, ma'am.
Respected Principal Madam, Professor Dr. Shutapa Mukherjee, respected Emeritus Professor, Sir Professor Dr. B.N. Chatterjee, Registrar Sir Dr. Shubhashish Pradhan, Head of the Departments, today's speaker Dr. Mohana Sundaram, Sir, my colleagues and dear participants. A very good afternoon to all of you. Though we are going through a tough time due to COVID-19 pandemic, but we can't stay away from our responsibilities and activities. We can't stop learning. Keeping that into our mind, Department of Electronics and Communication Engineering, BP Poddar Institute of Management and Technology, Kolkata, has organized a 3-day webinar series on sustainable energy commencing today. I am very much happy to welcome you all in this webinar series. As Sir and Madam have already told that the topic is very much relevant in the present situation of the world, where environmental pollution is increasing and resources of conventional energy are decreasing very rapidly. I am thankful to the organizer for choosing such a topic. We have eminent speakers from both academia and industries from who will enrich us during this 3 days program. I'm sure that we all are going to be benefited from the knowledge to be shared by the dominant experts and apply the acquired knowledge in our respective areas. I would like to say here something. As we know that during this COVID-19 pandemic, our loss is huge. To show our respect to those whom we have lost, I would like to request all to observe 1 minute silence. Can we please? Our time starts now. Thanks all.
Thank you.
So I'm sure that this webinar will help us to learn a lot of things. Thank you. Roshmita, please carry on.
Thank you, ma'am, for your kind words and kind gesture for remembering and paying tribute to all the near and dear ones whom every one of us has lost during tough times. Next, I would take the opportunity to request the convener of this webinar series, Dr. Orijit Shaha, to kindly address the forum. Orijit, please.
Respected Principal Madam, Professor Dr. Shutapa Mukherjee, Professor Emeritus and former Dean Academic Sir, Professor B.N. Chatterjee, HOD Madam of Department of Electronics and Communication Engineering, Dr. I.P. Majumdar, Registrar Sir, Dr. Shubhashish Pradhan, other distinguished participants, ladies and gentlemen. I am pleased to welcome you all to this 3-day webinar series on sustainable energy organized by the Department of Electronics and Communication Engineering, BPPIMT. We are all familiar with the fact that as the world progresses, more industrialization is inevitable, creating more usage of fossil fuels, and at the same time, deforestation is also happening in a fast pace. And in the process, we are increasing the level of pollution of our Mother Earth. In a recent report, it is predicted that abundant supplies of fossil fuels will end. In fact, it is said that at current rates of production, oil will run out in 47 years, natural gas in 48 years, and coal in 104 years. So the world is in search of new green energy sources to avoid pollution and make the world a better place to live. Keeping this in view, the webinar series is planned to aim at providing key inputs to the area of sustainable energy. And I am sure through this initiative, we are reaching out to many new practitioners, technologists, innovators in the area of sustainable energy or green energy. A warm welcome to you all. We are pleased to get such a good response where we have 134 registered participants, and I am confident that many more are following us on the YouTube live link. Dear colleagues, we all understand the importance of sustainable energy in our day-to-day lives and the ways in which they are transforming the world. Equally important is our collaboration in this great effort. And this is not just another scientific task. It is where policymakers, entrepreneurs, business people, financiers, and civil society come together in partnership. Distinguished participants, in this context, this webinar series will provide an insight in the areas of renewables for IoT, energy efficiency in digital filters, greening industrial facilities, non-conventional solar cells, energy management for hybrid electric vehicles. Here I want to share an information with you that our honorable speaker, Dr. Hari Babu, will not be available today due to some sudden urgent work. But at the same time, we are honored to have Dr. Mohana Sundaram sir from CDAC Bangalore to grace today's event and deliver the lecture. Ladies and gentlemen, I believe that by participating in this webinar, we are in the right place and the right time. Together, let us accelerate the exchange of ideas and scaling up of good practices. I am confident that you will find new ideas, fresh energy, and novel partnerships to sustain your efforts in support of sustainable energy. I wish you all a very successful webinar series. Thank you.
Thank you, Dr. Arijit Shah. Next, we move on to the next part of today's session, the most important part. I would like to invite Dr. Mohana Sundaram sir to take over the forum. Now, before he takes over the forum, I would take the opportunity to introduce sir to the participants and to the entire forum. Dr. Mohana Sundaram sir holds a PhD in electrical engineering from IIT Madras and has done his MTech in VLSI systems from NIT Trichy. Sir has an experience in silicon, glass, MEMS fabrication processes and characterization. He also has an experience in biosensor, MEMS chip design, mixed signal embedded system design, and FPGA-based system designs. He has worked as an IC design engineer in LSI Bangalore. Presently, sir is working as project engineer lead in CDAC Bangalore in the IoT group. He works on the design of sensors and systems for the smart water distribution network, air quality monitoring systems, indoor environment monitoring, calibration of sensors, and FPGA-based SoC design for low power and long-range IoT networks. Sir has published his research work on biosensor chip and electronic system design in IEEE sensors, analytical methods and sensors and actuators journals, and various other conference publications. Today, Sir will be talking about the IoT architecture in general, the need for renewable energy sources for IoT systems, potential renewable sources for smart cities applications, and some of the development activities at CDAC. So, quotes unquotes, Danish Kunich. It's time for a sustainable energy policy which puts consumers, the environment, human health, and peace first. So, without much further ado, I would request Sir and invite Sir to take over the forum. Thank you.
Thank you, madam. Am I audible to everybody?
Yes, sir.
Yeah. Thank you so much for inviting me to deliver this talk. So it was my manager who was supposed to give this talk. So since he could not, he had an urgent meeting, so I was called in. Anyway, it's a good opportunity for me to explain like what kind of activities that we do in CDAC. So let me introduce myself. My name is Mohana Sundaram. I'm working in CDAC Bangalore for the past 6 years now. So I'm working as a part of IoT group. So we do work on many IoT applications related to smart cities, such as water distribution, air quality, and we also work on agricultural applications, smart energy applications. These are the recent works that we have done. Smart postal kiosk that was made recently by our department, our group. So currently we are working on the SoC development of same IoT edge end node development. So let me share the slide and then we'll start continuing the discussion. Give me a moment. Yeah, is the slide visible?
Yes, sir. Yes, sir.
Yeah. So is it full screen now? I hope
No, sir, yet not.
I've made it full screen, but still not full screen.
Sir, is it in the slide viewer mode?
I made it full screen. Just a minute. I'll just stop sharing and yeah. Is it full screen now?
Yes, sir.
Yeah. So okay. So if I understand it right, we are talking about renewable energy sources, especially for IoT devices in this webinar. So since we are working in IoT group, we have I'll tell you I'll discuss some of the applications that we have developed in IoT domain. With the IoT technology, we have worked on many domains that we'll discuss use cases and the data that we have received. I'm not able to move the next slide. Yeah. Okay. So before I go on to the topic, I would like to tell something about CDAC. CDAC is Center for Development of Advanced Computing. It is a scientific society which comes under Ministry of Electronics and Information Technology. So our parent organization is MITI. CDAC is located in 12 centers in our country, major cities in our country. So CDAC has been working on multiple. It's initially started its work at supercomputers in early 90s, and then currently it has evolved itself in multiple domains with computing, a lot of computing, electronics, artificial intelligence, high performance computing, various other applications it has ventured into. So CDAC Bangalore especially works on high performance computing, big data analytics, and then where artificial intelligence is also used, and in IoT group VLSI domain. So in our group especially, we are for the past almost more than 10 years now, 2009. From 2009 we have been working on developing IoT devices. So we have an evolution of how we have done the IoT devices. So we'll see some of the devices in this series also. So before getting into the actual renewable energies and energy harvesting related for IoT applications, I would like to introduce something about IoT first. Then we'll understand the motivation why, what kind of energy is really required for this IoT nodes. What is that node we're talking about? Where is it coming? And all those things. Then we'll finally see some of the use cases. So Internet of Things, if you see, it is connecting anything, anytime, any place connectivity is what we're talking about. So the very basic building blocks or very backbone of this Internet of Things is sensing and actuating. So what we want to sense, there are so many parameters in this world to be sensed, especially when it comes to the environment or monitoring something in the environment, be it water or soil or air or anything. We need multiple sensors. So these sensors have to be monitored. I mean, sensors are helping us to monitor the actual parameter of interest. So the IoT devices are the devices which are meant to operate in very low power mode. So the power is what a very important factor here. So what we're talking about is a very low power small devices which monitor these parameters, like light intensity, for example, temperature, for example, relative humidity, soil moisture, kind of it. So I wanted to, as a person who is working in this an application such as an environment, my interest would be to monitor so many parameters that affects the environment, like weather parameters, wind speed, wind direction. So all these things are monitored by a huge equipment, huge instruments, probably currently in a sophisticated laboratory. But I wanted to monitor in a micro level, not in a macro level, but on a micro level. And then, multiples of such micro levels will give me an idea of how these parameters vary. So that is where our IoT devices come in handy. And these devices can be generally meant for wireless devices, but they can be wired also. So they monitor the parameter, the particular sense data, and then transmit the data. So if you see the genesis of IoT, this guy Kevin Ashton was the person who coined this term Internet of Things. So this is to refer to very uniquely identifiable objects, and then represent them in the internet-like structure, then transmit over the web. For example, if I wanted to know in my home, I want to automate everything. I want to know the condition of my room. What kind of very simple example is an air conditioner which monitors, when you set the temperature, it monitors the room temperature, and there's a feedback system which works and cools down the room. Very similarly, if I want to monitor remotely my the indoor condition of what kind of light intensity, what is lights turned on, have we turned on the water connections are off, or if I'm inside the home, what kind of ambience I may have, what kind of comfortness is there, what kind of carbon dioxide levels are there inside house, right? If you see a carbon dioxide outdoor, if you see it is about 400 to 450 ppm level. If carbon dioxide is there, if it goes up and down, and then finally it settles down to 400 to 450 ppm. But indoor carbon dioxide concentration, as long as people are there inside, it increases drastically. And you might have seen when people in a room where huge people are there, the carbon dioxide level, they breathe and the carbon dioxide level increases, and they probably, once it crosses 1000 ppm or so, people might doze off, right? So I wanted to know how much comfortness is there in my house inside. So I monitor temperature, relative humidity, carbon dioxide, even oxygen levels. So I wanted to monitor, even micro monitor all these parameters. So I need small devices to monitor that. So it started with that. So originally it was like RFID. RFID tags was in very close proximity. I was able to monitor remotely, very close proximity. But this advanced this IoT is talking about advanced connectivity, where systems and services, a number of protocols, various protocols, because there are certain standards which we are following, so that the coverage can be increased, the data reliability can be there, data loss will not be there. All this terminologies are, all these parameters are taken care of. So if you see the computing era, currently we are in ubiquitous computing world. So it started with big computers, mainframe computing facility where huge rooms, computers in the 80s, 90s, and then personal computers. We had that is a desktop computers. Now it is all smart devices. We have smart devices, handheld devices. There are so many number of sensors in our smartphones, right? If you see a simple smartphone itself has minimum 5 or 6 sensors, like accelerometers, temperature, maybe more. I'm just saying minimum 5, but it may be more. Temperature, relative humidity, magnetometer, gyroscopes, all these things are present inside the sensors and inside the smartphones. So that itself gives me a lot of idea how much, what is the weather today, how much of temperature is there inside my room. So all this. So this is it's all about computing anytime, anywhere kind of computing. So if you see the current trend from mainframes to smart things, I wanted to monitor everything I see, everything I work with, every enterprise I do, be it smart transport, or be it in agriculture, animal husbandry, or it can be a smart dustbin. I want to know how much of garbage is there. Is it full or empty? If it is full, I have to alert the authority to come and pick it up. Or if it is a vehicle, I want to know the air pressure. You see a current advanced cars, it has thousands of sensors in place, which keep monitoring so many parameters of the vehicle, and then display in the dashboard, and a lot of diagnosis happens based on that. So miniaturization is a key. A lot of miniaturization happens, and the cost also gets reduced. The time it gets reduced, the cost gets reduced, and the density becomes more, or the size of the devices becomes smaller. It goes in various kind of applications. Small devices can go in many kind of applications. The recent trends, if you see, now I have to come to the point where we really need the renewable energy sources. But before going there, we need to understand what kind of world we are into, where we are, why does it require to have it should be a holistic approach. It should not be we should see holistically what kind of things are surrounding it, so that everything gets important. So if you see industry 4.0 is a recent industry. So it started with industry 1.0, mechanical devices, make everything mechanical, and then industry 2.0 with electrical machineries, motors, pumps. And industry 3.0, it's all about electronics, computers, embedded systems, all those things. Now industry 4.0 is all talks about wireless connectivity. So with wired connectivity, what kind of speed, what kind of reliability the data devices give, the same kind of reliability and speed is what we are expecting at industry 4.0 also. So industry is slowly moving towards that. It cannot be done overnight, but it slowly evolves, and the automation happens seamlessly with or without the wire connectivity present in that. So what is the driving force? Driving force is basically sensor technology, where NEMS and MEMS kind of sensors are helping us to miniaturize, so that a lot of IoT sensors are used in IoT applications. Pressure sensors, barometric pressures sensors. So the small devices are available right now. Standardized package devices are available. Reliable devices are available. And then wireless charging is another area where places where we cannot access the wired medium. We need wireless charging to be done for the particular devices. And virtualization, currently what we are doing is virtualization, sitting in our own place and giving a talk. This pandemic has, this virtualization has really helped a lot of activities in this pandemic time. So in data analytics, it's a huge area. A lot of data is there. Once you put these sensors and IoT devices in a particular domain, you get a lot of data. What do you do with the data? How do you analyze the data? It should come out with meaningful information, it should evolve into right information and right kind of decisions should be taken. So a lot of analytics has to happen. And currently we are in the 5G world. Devices are coming up right now. Everything is standardized and slowly devices are coming up, and the testing has to start. Once the devices are ready, available, they talk about a lot of speed, high speed devices, high data rate, high density kind of devices, high density kind of gateways or towers, cell phone towers. So this is a 5G is all about cellular communication. So IoT related cellular is also there, that we'll talk about when we go to the next slides, few slides later. Then about AR, augmented reality, where a composite view of real environment will be superimposed on the virtual elements. If you're reading a book, you wanted to know book pictures, let's say a textbook or something which talks about the heart or any part of a body. I wanted to even see how it is automated. So there are tools which will even basically starts with the mobile phone, which there are some QR codes. If you scan that, you will have the you augment on top of it, so you read the book content as well as the automation of or the 3D picture of the heart, functionality of the heart, kind of things. In 3D printing, it's all for the digital integration with the customer. 3D printing is used in many applications where especially for IoT devices, 3D printing comes for a nice packaging that can also be there. I want a compact enclosure with so many arrangements that can be done on a 3D printing machine. 3D IoT devices does not stop at sensors. It has sensors and then connectivity from sensors to the devices, embedded devices. How does it connect? Through a glance. A lot of encapsulation has to happen through glance. IP grades are there, which will IP65, IP67 kind of compliance must be met, which are like dust proof, waterproof. So those kind of glance can be made out of this 3D printing. So IoT, if you see, it is a multidisciplinary application where a lot of electrical, mechanical, electronics, every domain, mechatronics, every domain comes into single umbrella kind of thing. So in artificial intelligence, again, that is a key buzzword right now. A lot of data. How do we do the how do we recreate the brain, a smart brain kind of thing, where machines think and they take decisions based on the observations that they have, based on the learnings they have. And another very important thing is security. Currently secured, when moment you put the device in the internet world, when you connect the device, there is a path given for the attackers to send their data. So the data that communicates, whatever data you monitor, temperature, pressure, that has to be securely transferred. So that gives an end-to-end data connectivity in a safe manner. So basic enablers are VLSI, where we a lot of chips, system on a chips kind of thing evolved out of it. Battery technology. So this is where the the energy concept comes in. So all the small devices, they have to work on energy. We can't keep plugging the wires to these devices because they go on the field. So they have to be battery enabled. So and then wireless communication standards are there. Already we are familiar with standards of smartphones. We have Wi-Fi connectivity, Bluetooth connectivity, and the cellular connectivity. All three connectivities are already a part of our smartphones. IoT initially started with personal area networks with IEEE 802.15.4 PHY and MAC layer protocol with ZigBee connectivity, and then 6LoWPAN connectivity that we'll see as you go there. Then MEMS for the sensor development, and the IPv6 are what we're talking about, the 6LoWPAN connectivity. So the data that we like to monitor should be transferred from the node or the IoT end node to the server or the internet. So this is the complete network edge internet connectivity, where we have end nodes as hosts where this applications are running, computer servers kind of applications. And then client server models are there. Then peer-to-peer model. A lot of connectivity happens in a big network like this. And it can be a mesh connectivity also. It may not be directly from node. It can be from mesh connectivity. So Internet of Things from an embedded engineering perspective is like there are things that has to be monitored, or that has to be processed with the help of sensors and actuators, processing and communication. This is what an IoT is all about. IoT end node is all about. This is a complete IoT structure, but this is an IoT end node. So this is where we are in. This is where this is the one which sits on the field, right? So this is the one which needs energy. So these are all battery powered. These are all not battery powered. They're all high power devices mostly. This gateway is the one which receives data from so many nodes, low power nodes. So this is usually powered, DC powered or AC powered, and then it goes to the internet, and then the gateway is like an aggregator which takes the data from multiple nodes and then sends it to the internet for processing, and we visualize the data. So here is where our IoT devices require energy for monitoring so many parameters of interest. So it becomes essential to harvest energy from the ambient sources, because the battery it should be battery powered for sure, but for sustainability the battery has to be recharged, right? So from where does it get recharged? We can't go and plug the power manually. It has to somehow take the energy from the ambient sources. So this is the architecture. Let's say it has a sensors, storage, process, radio. The storage and processing has become a microcontroller. Microcontroller plus radio has become a system on a chip. So this is a complete structure where we have a system on a chip, sensors, and the power separately. So this is a complete end node that we're talking about. The sensing, communication, computing happens all in one place, and then this data that is processed in this node is transferred to the gateway. So to give you some examples of the IoT processors that we have been using, ARM Cortex-M processors, Intel Quark processor, Intel Edison, Texas Instruments, MSP, starting from MSP 430, CC 2538, CC 3200. All these processors are usually used for this kind of wireless applications, be it a Zigbee kind of application or a Wi-Fi or a Bluetooth kind of applications. So very simple standard protocols that we are familiar with is Bluetooth, Wi-Fi connectivity. Initially, IoT started with Zigbee and 6LoWPAN. These are all for the personal area network protocols, wireless personal area network. It's for low power devices. So this protocol, this is a standard IEEE 802.15.4 is the MAC and 5 standard. On top of it, we have network and application stack with Zigbee, or another network application transport stack on 6LoWPAN on top of 15.4, 802.15.4. So and then apart from that, we have a LoRa kind of application, where this is talking about low power, long range networks. So the limitation with the Zigbee and 6LoWPAN kind of network does not transmit the data more than a kilometer or so. But if you want to transfer the data for more than a kilometer, Wi-Fi cannot be used. Bluetooth cannot be used. Wi-Fi is a power-hungry device. It consumes a lot of power. Bluetooth is again small, short-range networks. So this LoRa is meant for that. It has been evolving. So for the past 3 or 4 years, LoRa has been in the field, and this is promising. Like, it transfers the data about 5 kilometers from the end node to the gateway. Their modulation techniques are a little different. They use some chip modulation spectrum, which improves the the coverage, the distance that it transfers from the end node to the gateway. So this is kind of a star network. From every end node it goes to the gateway. But the ZigBee and 6LoWPAN are kind of mesh network. From node to node it transfers, and then finally it goes to the gateway. So some of the protocol standards and their network topologies, bandwidth. So there are a lot of things, parameters of interest, which certainly, depends. I mean, completely depends on the energy that is available at the source, at the end node. See, for example, the Bluetooth low energy devices, they operate at 2.4 gigahertz spectrum. So you need a power to transfer this RF wave of 2.4 gigahertz. So 2.4 gigahertz is a open ISM band spectrum, which is open in our country, is all or everywhere in the world. So 2.4 gigahertz is free to be transferred. This can be used as a free communication mode. This has 40 channels divided into 2 megahertz per channel space. It has a bit rate of about 1 megabits per second. It has a transmit power of 10 milliwatts. So there is a, for every packet that is transferred, it takes a huge amount of power. So battery, just keeping a battery will not be sufficient. Even if we keep if we can do one thing, we can keep a high density, high power battery, but the cost of it will go up. So we have to have a trade-off. These kind of Bluetooth applications are used in multiple applications where it has a, the smart band, that the smart watch or smart band, which monitors the acceleration, which gives the energy, how much of energy we burn. The wristband kind of applications, they are Bluetooth enabled, they transfer the data. And then the same 15.4 protocol, 802.15.4, which again works with 6LoWPAN or ZigBee kind of applications. They also operate at 2.4 gigahertz. So they transmit the data of about 250 kilobits per second. If it is a line of sight communication, they can transmit up to, if we keep a high power transmitter, we just boost up the transmitter power to about 1 watt or so, it can transmit up to a kilometer. That is the maximum power it is allowed for this application. 30 dB is the maximum power it can transmit. Not 1 watt, 30 dB is the maximum power it can transmit. So 6LoWPAN is the architecture that is recommended for energy kind of devices. It has become a standard for energy meters, where it is again a mesh kind of network. So the LoRa is what I was talking about, for a long range communication network, where it can transfer the data for about even 5 kilometers. For example, if you're working at water distribution network, where for a city kind of application, or for any small town kind of application, where the radius of the town, small town or anything is 5 kilometers, then this LoRa kind of application will work very well to transmit the data from every node of the water network to the gateway, and then to the server for further applications. Again, there are weightless N, weightless W, where weightless N is again, they talk about ISM band. Again, it's a free band, industrial, scientific, medical, where apart from 2.4, there is also sub-gigahertz bands, 868 in US, 868 in Europe and 900 in US. In our country, it is about 865 to 867 that is open. An ISM spectrum, license exempt spectrum. And weightless W is designed to operate in TV white spaces. TV white spaces are not open in our country, but in US, for example, TV white spaces are open. If you see the spectrum band, it is 400 to 800 megahertz. If you see the other one, sub-gigahertz, which is 800 megahertz or more, 2.4 gigahertz, right? So compared to 2.4 gigahertz, 400 to 800 is a very considerably smaller value. So the frequency, when the frequency goes down, the coverage becomes more and more. The wavelength is more, and then the coverage is more, and it has a huge capacity to transfer even video signals. So this recently Microsoft is working in in TV, using TV white spaces. They are working in agricultural applications, where they send a drone to capture video of the fields, agricultural fields. Unlike our country, every average farmer would have about 2 acres of land. But in US, farmers would be having hundreds of acres of land. So so they're monitoring that, it's a very huge thing. So they are heavily depending on the technology support. So Microsoft has put an application where they take a video using a drone of the entire field, and the video signals transferred in this TV white spaces. TV white spaces are nothing but TV channels. Between the two TV channels, there are unused spectrum. In that spectrum, they transmit this data. So the bandwidth is more, the coverage is more, so they can transfer the video data. What we were talking about is the small data, like temperature, humidity, is a very few kilobytes of data maximum, not more than that. But video signals are in megabytes and more, gigabytes kind of applications, right? We are talking about hundreds of bytes to maximum 1 kilobyte. That's what an IoT data is all about. Next, if you see what are the sensor interfaces that are available, simple analog, simple digital, signal conditioning, a lot of interfaces are there. If you see a gateway, we're not talking about energy here, but just to give you an idea of what kind of modules are present in a gateway, an application processor, IMX processor kind of processor is there. So not doing a lot of sensors and signal interfaces are connected to it. So an IoT platform is for various kind of applications, be it healthcare or consumer electronics, automotive, mobility kind of thing, right? So IoT platforms, big players are there now: Amazon Web Services, Google Cloud, Azure, Microsoft's Azure, so Oracle IoT. So a lot of people, big players are there who are providing the platform. So what we do is we have our own devices, and then we transfer the devices in this platform, store the data in the web server, in the servers, in the database, and then we can do a lot of analytics and plotting for visualization can be done. So once you hire the service, they provide the space, and then it can be done. So these are the devices that are developed by CDAC Bangalore. You see, this is a UB Sense, where sensors such as temperature, relative humidity, atmospheric pressure, light intensity, buzzer is also there, part of it. So all the sensors are present, and these are the devices that are developed by CDAC. UB-Mote is the one which works with first line network 15.4, what I was talking about, ZigBee or a 6-LoWPAN device. 802.15.4, on top of it we have ZigBee or 6-LoWPAN device, and then a Bluetooth device, BLE, Bluetooth low energy device, and then the Wi-Fi Mote. This is again, this sensor can be plugged into any of these modules. So we have a standard connector, 14-pin connector, where we, for an experimental purpose, we deliver this as a lab kit to multiple colleges. Many colleges we have delivered this as a lab kit, where we plug in this IoT UB Sense to this UB Mode, BLE Mode, Wi-Fi Mode, and the data from this is connected to this device, and then from each of the devices it is wirelessly transmitted to the gateway. So this is a multi-protocol gateway we have, which can talk to various protocols like Zigbee or 6LoWPAN, BLE, Wi-Fi, LoRa kind of application. So once it is transferred then to the gateway, from gateway again sends data to the cloud, and from the cloud it goes to the personal devices, our mobile phones or a tab or a laptop, where we visualize the data. So this is a very basic understanding of our applications. Here I've shown you with a UV sensors, a set of sensors, small device set of sensors. But here we have used in agricultural applications, water distribution, and then air quality monitoring, be it outdoor or indoor air quality monitoring, and the smart energy meter. So this just replaces the application, and then we get the use case. So the technical challenges that we have so far, we have seen many kind of IoT architectures, and in general we have seen IoT architecture and protocols, wireless protocols that are used, and what kind of hardware it has. You see how much of energy would be required to power up all these devices, power up all these hardware electronics. It has a lot of number crunching happens inside, right? It requires huge amount of power. I'll show you some of the examples where we measured how much of current it requires when we are transmitting a packet of data with the help of UV mode. When we are transmitting the data packets, we have monitored how much of current it takes, right? So we'll see that. So power system and energy harvesting is a big challenge. Apart from that, security is a very big challenge. Security and privacy issues. And then standardization is another bigger challenge. Everybody is coming out with their own standards. Standards as in the way we represent the data when it goes to the server, how it is represented. If it is of your unique standard, is unique everything, then it becomes very single platform to monitor the data. So now a lot of efforts have been made by our ministry to come out with a standard. In India, Urban Data Exchange format, I think it has come out with a standard, IODX standard, where everybody is asked to put in the standard at the higher level, in the application layer, not in the lower layers, in the application layer, and then transfer the data to the server. Right? Anyway, so that's all about the standards. So if you see the very major building blocks of any wireless sensor node, wireless sensor node as in the IoT device at the end node, right? For example, a huge water distribution network, I want to monitor the water quality, right? Water quality, let's say pH, water pH, water turbidity, or a chlorine, how much of chlorine is present in water. So I need a small device, I need a sensor which monitors that. The sensor gives me an electrical signal that has to be connected to a microcontroller, and then through some interface, be it a GPIO or ADC or UART or I2C kind of interface. And then it's stored in the memory. Once it's stored, and then a radio module which transmits the data at 2.4, for example, 2.4 gigahertz with Wi-Fi or a Bluetooth or a Zigbee kind of wireless protocol, right? And then, of course, the sensors and actuators are the ones which is connected to the microcontroller. And microcontroller gives signals to the actuators too. Let's say, for example, water, to actuate the valves, open the valves and let the water in. Then sensors are the one which monitors the pressure, water pressure. So all this signal transfer, signal conditioning requires huge amount of power, right? Power sources and power management is a big thing. This is like a pictorial representation of a generic sensor node, IoT node, where power supply module is a major one. It uses a DC to DC converter So there's a power supply directly we can plug in a DC from a DC adapter, can directly plug in a stable DC line, or from a battery we can power, right? Or it can even power from a battery with smaller voltage, so there can be a step up from a DC to DC converter, can power the entire node. So the sensor module, so it has to power the sensor module, the processor module, the radio. It takes a huge amount of power. So whenever it senses and transfers the data, when it's transferring the RF signal, at that time it takes a huge amount of current. Right? We'll see in that experiment how much of the. So this is like giving an example of typically how much of power is consumed by a laptop or a mobile phone or a calculator. What we're talking about is few milliwatts of power, right? At the IoT end nodes, few milliwatts of power. So why do we need now this much of power is consumed, but the battery cannot sustain for a longer time with the capacity it has, right? It has to be recharged. As we increase the network and the number of devices, replacing each and every battery is a very Herculean task, right? Once it goes to the field, just imagine a water distribution system in one city or even a small village, right? Every street has a connection, every street has a water pipeline. So we need to monitor the pressure of water, right? And a flow meter have to be put, water flow rate, water pressure, and there can be multiple water storage tanks, so water volume in that. There can be control valves, on-off status of the control valves. So, and then quality of water. So all these things, a huge number of parameters, and then every node has to monitor probably, for example, water quality. If you put one node to monitor pH, turbidity, free residual chlorine, TDS, with the nitrate, these are the pollutants, water pollutants. The number of parameters goes up, the battery consumption increases, right? The number of frequency of transmission increases. For example, if I want to transmit the data every 1 minute, or if I want to transmit data every 1 day, and that is a different thing. But for a water kind of application, I want to constantly monitor. Typically, once in 15 minutes, it has to be transferred, or even more. I mean, frequency has to be increased. So in that case, what the battery gets exhausted very quickly. So it is necessary to scavenge energy or to harvest energy from the ambient sources to keep recharging the battery, right? So the possible sources of energy sources are mechanical. These are all very common things, but how do we use it for our IoT devices is a big question. Mechanical energy, thermal, light energy, electromagnetic, right? Mechanical energy is basically vibration energy, vibrations which like piezoelectric, which converts the vibrations to electrical energy. Thermal energy, light energy. Thermal energy is the one which from the waste furnaces, heater, friction. How do we convert thermal to the electrical energy? And then light energy, of course, is very famous, photovoltaic, solar based, which is very promising, compared to any other energy scavenging. Solar energy scavenging is very promising for IoT kind of applications. Basically in RF, from energy harvesting from RF waves, from the nearby RF waves. Again, a natural form of energy is wind, water flow, ocean currents. These kind of energy can also be harvested if the sensors are present in their location. For example, underwater communication, right, in the sea happens with IoT devices. The same ocean currents can be used to harvest energy. The human body itself can produce a lot of static energy and mechanic. It can generate naturally from biofields, right? Walking, sitting, it produce a lot of energy that can be also stored and used up. Other forms of energies are chemical and biological sources. I can give some of the examples. I'll give you because we have worked, as one of the professors mentioned, we have a little worked with bioenergy also. That we'll talk about when you go to that example. So energy harvesting are like, again, piezoelectric, photovoltaic or the solar based, thermoelectric generator, electrostatic is, or let's say piezoelectric is again vibration to the mechanical vibrations to electrical energy. Photovoltaic is light intensity, solar light, it generates the energy. Thermoelectric energy is like Seebeck effect, which temperature difference could produce electricity. Electrostatic is capacitance, change of any of the capacitance property producing electricity. Then vibration, these are the source of energy: vibration, thermal, solar, human input. And another residual energy is like RF energy, EM or RF based of energy. Again, it is just to emphasize the ways in which it can be produced. The cantilever piezoelectric, for example, cantilevers, especially when it comes to miniaturized devices, MEMS-based devices, MEMS-based cantilever devices, where piezoelectric materials are coated on top of the cantilever structures, where energy can be harvested. Where micro pump, for example, requires energy, right, to actuate so it can in fact generate the energy and then again actuate the micro pumps, the miniaturized devices. So photovoltaic is again solar based, where it can be a crystalline silicon which produces more efficient energy, 15 to 20% of energy. But if it is a polycrystalline, it is little lesser. So crystalline silicon, it is expensive compared to polysilicon. I'll give you one example of the cost of it. For example, when I was working with the 3-inch silicon wafer, a small 3-inch diameter silicon wafer of about I think about 350 to 400 micron thickness. 350 to 400 micron thickness. 3-inch crystalline silicon wafer is about $25 each. So you can imagine the cost is very huge when you want to put a solar panel. Of course, when you scale up, the cost should go down. I was talking about a 3-inch silicon wafer where we purchased about 25 wafers. But once you scale it up, the price will go down. But nevertheless, I just want to emphasize how much of cost it is. Again, polycrystalline silicons may be a little lesser expensive, but the efficiency is also a little lesser compared to that. Thermoelectric, on the other hand, is again.
Good afternoon, sir.
Yeah, tell me, please.
Actually, I have one query, sir.
Yeah, please tell me.
Sir, you have shown the efficiency. Actually, I have query on that. Is this a laboratory research efficiency, or is it laboratory efficiency, or it is a commercial efficiency?
No, this is the data taken from the commercial thing. Yeah.
Okay. But what about monocrystalline, sir?
That data I'm not having. We are not.
Okay.
Yeah.
Okay, sir. Thank you.
So to interrupt you, in the middle, I would request the participants to take up the questions at the end of the session. We will have a separate session for questions and answers, and then sir can actually take the time to answer to all your queries.
Okay, madam.
Thank you, sir. You may please proceed.
Yeah, ma'am. Thank you. Thank you so much. Yeah, so when it comes to an thermoelectric generators, two dissimilar metals exposed to the temperature gradient. So we have made an experiment for this. We kept one junction at cold and another junction at hot and cold junction we were able to generate. some energy. That experiment results when it comes, I'll show you there. So again, energy harvesters, basically vibration, solar, RF, thermoelectric generators. These are just given examples of where it is really required. Vibrations, transportation, majorly vibrations are used in industrial applications. Vibration sources are available where we can harvest the energy. Solar and multiple locations. So out of all these things, vibration, solar, RF, and thermoelectric, from the researchers, what I've heard so far, especially for the IoT kind of applications, solar is most promising. Others are very, the time it takes to charge the batteries are huge because the efficiency is very less. Even compared to solar, the efficiency are even lesser for RF and vibrations and thermoelectric. Thermoelectric, on the other hand, we need a huge temperature difference to get some kind of efficiency. So based on a lot of researchers currently, also solar is most promising one. Okay, so the major building blocks of energy harvesting systems are conversion electronics, where energy from any source any resource has to be converted into voltage signal, right? That is a major thing, and it has to be made usable energy format, right? So it needs a lot of electronics, charge pump kind of electronics, charge control circuitry, where from the energy takes for example, solar, it will not be constant. Light intensity will not be constant. It varies over time. So, but irrespective of that, the charge control takes care of that and keeps charging the batteries. So batteries are again the storage devices which accumulates this collected charges and stores the charges in it. And the lifetime of it is again a major thing. What is expected right now? So some of the devices, recent devices which you have noticed is about, they say we have a IoT node for monitoring the water flow, right? Water flow, and they say for about 5 years it can work without changing the batteries. So they work in a very low power mode. Ultrasonic based. What we have seen recently is an ultrasonic based water meter, right, which works at a very low power mode, and the battery of it will come for 5 years. How is it even possible? Because they have water anyway flows through the pipe, right? So there's a turbine generator also placed in line with the flow meter. So when the flow meter moves, there's a turbine moves, and because of that, when the water current, the turbine moves and electricity is produced. There's small micro or nano kind of charging happens slowly, and then it keeps recharging the batteries. So based on the pressure of water and the flow rate of the water, if the pressure is more and the flow rate is more, the battery gets charged faster. So that's how we maintain the lifetime of the battery for 5 years. For example, in a smart city kind of application where we are talking about replacing all the water meters in our country with smart water meters. This is the kind of water meter we're looking for, right? There should not be any wire coming to the meter. If the meter is wired, it might not be reliable, right? It might get cut. The water meters currently, if you imagine the kind of water meters in which kind of place it is kept, it is messy, it is completely filled with water, right? So we cannot afford to keep running the wires. So the device should be compact. It should go in line with the pipe, and the battery should be at least working for 5 years. And the battery status also is transmitted to the server. So when we know when we have to change the batteries, right? So at the time we get the information and we change the batteries. So that's it. So that kind of application is what we're talking about. That is where we are the ambient energy harvesting is become very important. So primary batteries are here. Some examples are given: zinc, air, lithium, alkaline. So the energy density is more for zinc air kind of batteries. Lithium battery, for example, has more longer life compared to the other batteries. And then secondary battery storage. So when we talk about this primary storages and secondary storages are again rechargeable batteries, which has to be kept. So for any IoT kind of network, relying on one particular renewable energy sources is becoming a problem. So it will be better if you are depending on more than one energy source. For example, in water kind of application only, right? When you're monitoring the water flow, we can harvest the energy through solar. That's a primary source. And then secondary sources can be, other sources can be water. From the water flow itself, we can harvest the energy and store it in the batteries, right? So relying on one particular, for example, solar might not be there continuously for 2 or 3 days due to weather change. So in that case, the battery should not get depleted and deteriorated. So the battery on one hand should be able to sustain itself for at least 2 days to 3 days. If the battery can work for more and more time, the cost will go up. If you want to reduce the cost of the batteries, then in that case, we have to put more than one way of recharging the battery. And the energy delivery, we talk about energy delivery, delivers the current and voltage levels required for the application. There can be a boost capacitor which delivers high current to the battery. So this electronic circuitry will come in handy. For example, some of the energy consumption is given by a microcontroller, MSP 430, for example, at 1 megahertz 3 volt application. It takes 1.2 milliwatts of power. It takes. In the deepest sleep mode, it takes about 0.3 microwatts, right? Atmel, on the other hand, it takes about 15 milliwatts of active energy. So in the sleep mode, it takes about 75 microwatts. So the energy consumption just by a microcontroller is this much, and the sensor also takes some energy, right? So and the communication device also takes some energy, where it has to transmit at 2.4 gigahertz. So this is an example of our sensor board where we have light intensity, smoke sensor, humidity sensor, and accelerometer, which are connected to the IoT sensor. This is the node, right? IoT node. The light sensor is again gives a digital output where it monitors the intensity of light. Of course, IR compensation is also part of it. There's an ADC which takes the analog input and converts into digital uses. And then accelerometer, we're all aware of it because we have it in our mobile phone. It's a capacitance-based measurement where there is a fixed beam, there's a moving one based on the vibrations. There is an accelerator. Accelerator is kept in all 3 directions, X, Y, Z. So based on the X direction, Y direction, and Z direction, the capacitance changes, and then we get the change in capacitance is mapped to the change in acceleration. Change in capacitance is measured as a change in charge, and then from the change in charge, it is the electrical signals are sent. And so the electrical signal sent is proportional to change in acceleration. Okay. Then like relative humidity and temperature sensors are also part of it. So these are the 4 devices, sensor boards, and then components. If you see how, so every device would take huge amount of power, right? So some kind of awareness is required. How does it self-aware and controls, right? How does it self-aware how much of power it is consuming, and how do we reduce? How does it? So we have to instruct. We have to write a firmware such that it has to go to sleep mode or deep sleep mode when it is not transmitting ideal conditions. All those awareness has to be created. Let's say if there's a power, the power is very less, instead of transmitting continuously, the firmware should be written intelligently such that Whenever the power is available, only it transmits the data. Till that time, it stores the data in the local battery, local storage device, right? So in that case, it does not die, because I want the data. At the end of the day, I want the data. So if it just transmits the data irrespective of whether it has a power or not, it will die down and it will lose my connectivity is lost. Again, someone has to physically go on address to make it up, right? Instead of that, if I can get somehow the energy to, intelligence to store the data in the memory, and then once the power is available, transfer the data. So kind of awareness has to be created. Some of the basic definitions before going to the next slides are given here. Mode is a small battery operated sensor. This is what I was talking about, IoT end node, right? This mode is what I was talking about. And wireless sensor network is an autonomous network which monitors all these parameters and transfers the data. Energy harvesting is a process of converting natural ambient light, such as light, vibration, into an electric energy, like solar, RF, piezoelectric, all those things. MPPT is, you must be knowing, maximum power point of solar panel. Self-powering is the process of generating required energy by the system through the environment, right? From the harvesting from the ambient sources. So fuel gauge is a device that gives the information about on the amount of charge available inside. So it just monitors the current storage charge and gives an awareness of how much charge is left. How do we control? The firmware takes use of this data and then intelligently apply an algorithm to judiciously use the power that it has, right? Battery management system is the one which controls all this charge transfer from the primary sources, and it should avoid overheating, all those things. The batteries, LDOs, switching DC to DC converters, then DVS, all these things are the primary parameters, LDO based solutions, which are the primary building blocks of any power converter. So I'll give you an example of how much of power is consumed from our mode, right? So this is our mode UV mode, which was originally made by CDAC. You see this is a graph. So this is the amount of current that is consumed whenever it is transmitting one packet, right? So when it takes about 27.78 RMS current, milliamperes, 27.7 milliamperes of current it takes, right, to transfer particular bytes of data packet. So if it keeps transmitting, when the frequency is increased, if the transmitting frequency increases, the current, huge amount of current is taken from the battery, and the battery soon dies, right? So some kind of scavenging is again required. This is what, to emphasize it, I'm just put the slide again. It needs huge scavenging from the ambient sources, because when we are transmitting each and every packet, the battery gets depleted and it has to be recharged again and again, so that we don't have to go and address in person every time. Because once you have the field, right, devices, we're talking about is lakhs and lakhs of devices, not few hundreds or thousands. Right? IoT applications require lakhs and lakhs of devices which are to be micro monitored. So in typical solar input and mode, between that it has a DC to DC converter, lithium-ion battery, charges lithium-ion battery, lithium-ion polymer battery, or it's a typical architecture where the energy gets stored in the battery and the mode, the IoT end nodes is it. Some of the examples of the battery, rechargeable batteries are given here. Compared to a sealed lead into motor vehicles, which is the density of 60 watt-hour per kilogram. The lithium-ion polymer has more density, like 260 watt-hour per kilogram. Right? So what is the problem with this energy scavenging? Just one energy scavenging is not sufficient. If possible, we can have more and more energy. With one energy, if a battery has a lot of storage capacity, then it is fine. But then the cost will go up. So everything has to be a trade-off, right? So for water kind of application, as I mentioned earlier, we can have both solar as well as water-based energy harvesting. If possible, wind-based harvesting can also be done, right? So How to solve it? Have to add primary sources, more and more primary sources, no more than one at least, and then batteries of high quality, high storage has to be used. Some thermal energy harvesting, some experiments we have done with thermoelectric generators, which works on temperature difference, gives the current, produces the voltage. There's a heat source, there's a cold source, and then this is kept in between that. There's a general charge circuitry what we have produced is about 5-degree change in temperature. We were able to produce 0.4 at 2.3 0.4 watts, milliwatts of energy. At 35-degree temperature difference, we are able to produce at least 3.8. At 3.3 volts, it is 3.3 watts of energy it is able to produce with the commercially available thermoelectric generators. So this is an experimental setup where cold junction and hot junction are kept, and then we have monitored the time it takes, how much time it takes to charge the batteries. So in a battery capacity of 250 milliampere hour for 15 minutes duration, about 7 degrees temperature difference, we were able to initially it was 22%, it was about 24%, 2% increase for 15 minutes. And for a battery of about 1050 milliampere hour, for 4 minutes duration, it is about for a temperature difference of 9 degrees, it was increasing from 62% to 65%. Huge temperature difference percentage increase was there. So when it comes to the RF domain, we have done an experiment with an RF. So RF is basically, how do we harvest RF energy? We need a good antenna to receive the RF signals. Then from our RF signals antenna, we need to convert into proper DC voltage, and then the DC voltage has to be stabilized and then stored in the battery.
It seems there's some kind of network glitch, so I would request the parties bear with us and hold on. Sir will be joining with us shortly.
Arundhati, can you contact sir?
Yes, ma'am. Yes, ma'am. I'm calling him.
I'm sorry, I did not notice. I got disconnected. Am I audible now?
Yes, sir.
Okay. So I don't know when I got disconnected. This slide or before that?
So before this.
This slide or even before?
Before this.
What I was talking about is the energy. How
so
we
connected the page number 70.
70 is it?
Yes.
That I did not notice. Okay, so RF, apart from thermal energy, we also experimented with RF energy harvesting. But even this one was not. It was not promising. So it was additionally requiring another power source. So antenna was used. Matching network was used from antenna. We got the RF signals, RF to DC converter, then DC to DC converter to charge the batteries. But this was requiring additional power supply. So we have just done a simulation just to see how much of this. We've replaced this antenna with AC source with a series resistance. So where we could notice about 0.7 volts of a voltage it can produce. So we have done an experiment connecting keeping the RF source and an antenna to harvest the energy. So this was a antenna kept and we were charging the batteries. DC-DC converters were present. So what I was telling is it was not that promising. We could see more and more energy harvesting with the solar, and then the piezo, and then the RF. More solar, piezo, thermal, and then the RF. This is the way in which we could harvest energy. So even in piezo, if you see that there is no much change from initial state of charge to final state of charge for a certain duration of 1 hour or so. So this was a typical solar power supply module where we have DC-DC boost converter batteries, fuel gauge. This is a complete setup that we've used. Additionally, we have a AA battery that were also used. Even for the reliable communication, if it fails due to some reason, at least we should need an additional battery to power up the node. Right? And some of the applications, I think I should quickly go through. Some of the applications that we have worked with is one of the applications is the agricultural application, where we use solar energy harvesting primary. This was done along with CDAC Hyderabad. This was deployed in agricultural field in Anantapur district in Andhra Pradesh, where if you can see we were monitoring soil temperature, leaf wetness, ambient light, ambient relative humidity, ambient temperature. And this was the sensor node, and then this is a solar panel that's fixed. So this was deployed in an agricultural field. Here all these 4 parameters are monitored. So you can see a remote location, right? It definitely requires the solar energy. It cannot be powered. This was done in about 400 acres of land. About 74 wireless sensor nodes. So this was monitoring some of the parameters, soil and micro. This was basically microclimate monitoring for the pest and disease forewarning. Right? There was a leaf miner pest disease. There was some disease. This forewarning was given with all this sense. So where the solar energy harvest really helped us in deploying it deploying in the field and taking the data for sufficient longer duration, right? For entire season of groundnut cultivation. The leaf miner, leaf spot diseases that were monitored, the forewarning were given, and this was like about 450 acres of land, and 162 registered farmers were there. About 74 end nodes were placed in 5 villages, and some 50 farmers were indirectly benefited out of it. So the wireless sensor nodes were placed in all these locations, which were giving advisories to the farmers through scheduled advisories, specific advisories, and when it has to be, when the pest has to spread. So there's one was given. So chances of pest attack, chance of disease attack was given. So at that time, there was a calculated and sufficient pesticides were used, not enormous and blanket pesticides were used. They were able to save a lot of money in eradicating this disease and pests. So that was the benefits given. Then another one I was talking about the bioenergy. So this spirulina, this one we collaborated with CTI Mysore, in which they were manufacturing the spirulina. Spirulina is used as a food for protein-rich food and used as a supplement. It is also used as a bioenergy. Some reason it consumes a lot of carbon. Right? It is also consuming a lot of carbon. Sequestration also happens in this. This one used as a biofuel as a carbon sequestration device. Right? It takes up a lot of carbon dioxide into it for its growth. Right? So in that way, it helps in reducing the carbon footprints. So this is a setup where we are monitoring multiples of parameters and helping in the food production. Another one is monitoring the vegetable, for example, tomatoes, which when it grows in beds in trucks, we want to monitor the condition in which it goes, like temperature and humidity, from the source to the department the stores it reaches, in what condition it was transmitted. Right, what kind of ethylene concentration was there? So based on that, we can know the freshness. Some analytics, we were planning to build some analytics which will give us an idea of how much fresh it is, how much safe it is. This is another application of polyhouse, where again we are monitoring the temperature and humidity inside the polyhouse. Where IIHR, in the Institute of Horticulture Research, we are doing this experiment where they were doing this tomatoes as well as cucumber cultivation. Right? So again, since it is a transparent polyhouse, again solar panels to generate the energy. Solar panels are there at every node to generate the energy and transfer the data to the gateway. And this is a water application, typical water distribution system where water goes to the treatment plant, and this is the starting point of any town or a city, where water is stored in ground level storage, and from every ground level it goes to the elevated storages. From elevated storage, we mount in a particular terrain condition, the water is, or through gravity or through electrical pumps, the water is sent to the every area, right? Every household. So here, where a lot of level, pressure, quality sensors are there. So this is where a challenge was announced by CDAC, MIT, and Jal Jeevan Mission to come up with for the startups, it's my MSMEs, to come up with solutions for villages. Where CDAC Bangalore has implemented this change in the month of February, and currently those people who the challenge are deploying this complete solution in each one about 25 villages in our country. So So 4 or 5 winners, about 100, more than 100 villages, the solution can be deployed. So each node, what they're doing is a solar-based energy harvesting. So about almost for 2 days, it should be able to sustain without any power. The battery should be able to sustain the power. In that condition, they have made the devices and they're deploying currently almost 100 villages in the country. Right? And this is about portable weather station monitoring. Again, this one was deployed, supplied to IISc experiment in architecture department. So this one has the weather, wind speed, wind direction, temperature, and humidity for parameters that were monitored. And then this is an individual node powered by solar panel, right? Solar powered. And this is our outdoor air quality monitoring system where we monitor nitrogen dioxide, ammonia, carbon monoxide, and ozone. Right? These are the 4 parameters that are monitored. So this is when we are supplying with all battery powered as well as the AC supply. Right? Whenever possible, it can harvest the energy, solar energy, and store it in the battery. Whenever solar power is not there, it can directly take it from the AC supply. Last application where monitoring the airport terminal buildings with these are the parameters that are monitored: temperature, relative humidity, energy, carbon dioxide, light intensity, dust particles, of course. So this is the scope for energy harvesting was lesser compared because it is completely indoor application. But then we were able to try some of the RF energy sources of harvesting, but it was not because it was taking more and more time to recharge the batteries, right? And this is a very recent deployment that we have done for ecology interest. We have deployed, the nodes where in the Western Ghats region, where this was able to monitor the sound of birds, right? And there are solar panels which charges their batteries again. So this was to find out the condition of the bird, what kind of bird there and condition it is it healthy or not? All this in collaboration with IASCR and IIT Mandi, this work is being done and currently being deployed and monitored. I think these are the things. I think, yeah. Really. Yeah, so these are the places, some of the applications where we have utilized this energy harvesting efficiently, because without which it was not possible to supply, especially these kind of forest kind of applications. There's no scope for getting energy unless we harvest something, right? Yeah. Thank you so much for all the time and patience, patiently listening to my lecture. Thank you so much. Thank you. If you have any questions?
Yes, sir. Thank you, sir. I would request the participants to please come forward with the questions. You can write the questions in the chat box and I can put forward the questions to sir. So there was a question from Nimay Chandragiri previously. How IoT can be used in agronomy for both power and crops production?
For both power and what?
Crops production. Crops production.
Okay. Yeah, so it is again basically monitoring the parameters, right? So IoT. IoT is the one which I was talking about. TV white spaces where Microsoft is being used, right? Microsoft has been working on. They were monitoring the complete field using the drone kind of images. They take the images and they do a lot of analytics on it. The harvest cycle or the ripenness, how much ripen it is, what is the time for harvest, what kind of yield it has. All these things are done using a lot of video analytics, image analytics. But then IoT helps in just monitoring the data be it an image or a video or mostly not video. IoT is all about small data. As long as it works in 2.4 gigahertz kind of application, when it goes lower frequencies, it can even transmit the video images, and a lot of analytics can be done with that. So if crop yield can be monitored, harvest cycle can be monitored, those kind of applications.
Thank you, sir. There's another question put by Ramesh Kumar. IoT makes the system smart, but in future, large number of IoT devices will also produce a great deal of electronic waste. What about if e-waste materials cannot be recycled?
No, I think some way to tackle this e-waste recycle has to happen. Otherwise, it's going to be a huge mess, right? 5G coming, 5G is also coming up. A lot of cellular phones will go out of. The current smartphones will not be useful. The updated phones have to be used, right? So a lot of e-waste recycling plants has to open and it has to start. I think technologies are there. When the funding support is there, a lot of industries can take the technology from a lot of CSIR, DRDO kind of organizations have the technology. I believe the technology has to be transferred to them and then it has to be recycled.
Thank you, sir. Any more questions from the participants? So it seems there are no more questions from the participants.
Okay.
Since we have come to the end of this session, we are indeed grateful and really honored to have you, sir, with us for this enlightening and enriching experience you gave us all, and taking us through all the activities which are carried on with CDAC and all the new relevant topics which the researchers and the students can ponder upon. Next now, I would request our technical team to kindly present a certificate of appreciation. Sir, on behalf of the Department of Electronics and Communication Engineering, BPPIMT Institute of Management and Technology, we all would once again thank you for being the invited speaker today for the 3-day webinar series on sustainable energy organized by the Department of Electronics and Communication Engineering, BPPIMT Institute of Management and Technology. Thank you, sir. It was indeed a pleasure having you with you all with us.
Thank you so much, everyone, for patiently listening to me. It is almost, I think, 1.5 hours. Thank you. I hope at least some information was useful to you. Thank you so much. Yeah.
Thank you, sir, once again. The feedback link has been shared in the WhatsApp group. So participants, please fill up the feedback form. And I would request everybody to kindly switch on the video so that we can have a photo shot or screenshot with sir. Is it done, Prashanjit? Yeah. Thank you, sir. Thank you once again. All the participants, please fill up the feedback form.
Rashmita, please mention tomorrow's time.
Yeah, I'm just mentioning it.
Thank you so much. Thank you.
Okay, this is again an information, very important information for all the participants. Tomorrow we will be starting the session sharp at 2 p.m. till 3:30. Tomorrow we have with us Professor Mrityunjay Chakraborty sir, who will be delivering his speech tomorrow. And then we again from 3:30 p.m. to 5 p.m. we have another speaker with us, Mrs. Disha Bhattacharya, Senior Engineer Qualcomm. She will be delivering her speech from 3:30 to 5 p.m. onwards. So participants, please be sharp on time, and looking forward to meet you all tomorrow again. Just a reminder, please fill up the feedback form, which is already, the link is already been placed in the chat box. Thank you all once again.
Thank you, sir, for your nice presentation.
Thank you, sir.
Thank you,
so
sir,
much.
for this informative session. Thank you.
Thank you, ma'am. Thank you so much.